Basically today I'm Marina Zapater. I come from the Embedded Systems Lab from EPFL in Switzerland. And what I will be telling you a little bit about is about the 3D-ICE simulator. Basically, 3D-ICE is a thermal simulator. Just to give you a very, very quick overview, what we want to do with 3D-ICE is we want to simulate, given some power of a certain chip, for a 2D or a 3D chip, what is the temperature that we are going to obtain. So it's basically a thermal simulator. In this talk, I'll tell you a little bit about why we are doing this, why is it important, and what is our roadmap, and what is our current status also. Okay? So basically, let me start by the motivation, right? So why are we doing this work? So as you know, as you perfectly know, we are seeing a dramatic increase on the computing requirements, which means that we can face that in two different ways. Either we can come and put more chips to do a certain workload, and we build these huge data centers in which we put lots of chips, lots of processors into servers, and lots of servers into the data center, or at the same time, because in fact we're doing both, right, is having more processors on the same chip, which is very good because we do more stuff, but it means that we have chips that consume a lot of energy. Okay? So the thing is that so far, we were happy with that. Let's say that while Moore's law was working, we were having more and more transistors per chip, and that was okay. We were having more and more operations per second with more transistors. So we were going from this first processors, right, with not doing so many operations per second, and increasing the number of transistors per chip, also increasing the number of cores per chip, until reaching up to 80 cores or even more on new processors, right? That's very good. The only issue is that we are still very far from efficiency. Efficiency understood as we're very far still from doing as much computations as the brain can do with a very low energy consumption, basically. And the main issue of that, or one of the main issues of that, is that we have a high energy consumption, and also we are bottlenecked. How are we bottlenecked? So basically, we're bottlenecked by the memory. So our processors do a lot of stuff. They get bottlenecked on the memory. So what we did is, OK, let's go from 2D chips to 3D chips, which is a very good idea. So we stack layers of chips, one on top of the other, and we get a 3D chip. Issue of that, well, more transistors, more power density, and then more power density, more temperature, which means that we may start having reliability issues, right? So we are going to have hotspots on our chip. We need to be aware of those hotspots. We need to prevent them in order to increase the reliability of our systems. So the thing is, it's not only a matter of having hotspots, right, of one of the cores getting too warm. It's a matter also of these hotspots are not going to be uniform. They're going to depend a lot on the workload. And from many years now, we've been working on how do you manage hotspots on a chip, how can you make them work better. And the issue is, it's already a challenge when it's a 2D chip, so when it's one layer only. The issue is, OK, if we go and stack even more chips and we make it 3D, it gets even worse, right? So when you see how does the stack look, so you're getting worse and worse, of course, as long as you stack more and more chips. With a 2D chip, we know that fan-based cooling, it's inefficient, but it works, okay? But as you stack more layers, you start having issues on how do I cool down this system, okay? And of course, then you have higher chances of thermal issues. And if you have higher chances of thermal issues, okay, today your processor won't be destroyed. The CPU will simply throttle the frequency, and you'll be working at a lower frequency, which is sad, right? Because if we have processors that are able to reach 3.6 gigahertz, you don't want to be working at 3. Okay? So basically, we need to manage this. So a while ago already in our lab, we did some research. So this is research that we are doing together with IBM, so that they help us understand what are the challenges, how to face them, et cetera, from an industrial standpoint. And we did a very basic example, well, not so basic at that point, but basic stacking a 3D chip, 5 layers. Here, it was not real processors. It was only some heaters to understand how the heat propagation worked. And the thing is, we put 50 heat sources, basically, of different sizes, and we injected some watts per layer on this 5-tier chip. And what you see is, OK, at some layer, so one on top of the other, second layer, we have some temperature distribution. But as you go up through the tiers, because of the heat propagation, what you're getting is more and more hotspots, which is expected, right? I mean, because in the end, you're simply stacking things one on top of the other that consume a lot of power, and you're not thinking anything fancy on the cooling side. So the thing gets hot. So it's large and non-uniform heat propagation. And you can achieve really very high temperatures on the top tires, so up to 130 degrees, which of course is too much for any technology today. So the thing is, it's a challenge. So how do we first understand what's the challenge, right? So our first approach was we need modeling tools for 3D chips. Not only for 2D chips, they are a challenge, but also for 3D chips because that's what's going to come, right? The goal here, as I was saying at the very beginning, was we want to obtain what is the chip temperature, not only at this instant, but through time and through space. So basically, it's understanding what is the temperature at each part of the chip floor plan at each instant of time. And we can do that for normal fan-based cooling or for a heatsink, basically, in which you can have the chip. So you have the PCB, you have the chip, okay? And on top of that, you can put a heat spreader and a heatsink. And the thing is that if you want to compute what's the temperature, you get into having to calculate some fancy equations about heat propagation in solids. That's doable, that's been done, right? So you can solve these equations. Issue is when you try to put that together with power, you can start on the loop of solving what's going to be the temperature attained when I put a certain power. The only complexity here is that if you don't do anything else rather than solving the equations, basically, it's a very complex computational problem. So as a result of this, instead of simply putting together the equations and trying to solve them, what came was the first tools that were able to do what we call compact RC-based models. What is RC? RC is resistance and capacitances. So basically, what we are going to do in this respect is, so we know what our system is, and we are going to simulate our system as a bunch of resistances and capacitors. So we will create like a network, okay? And we will, instead of solving directly the heat equations, we convert our heat equations into resistances and capacitors properly connected, and we will simulate our system like that. So, and we will be also simulating the coupling between layers. So you can have different layers, like a silicon cell, for example, or a copper cell, and they are connected with resistances and capacitors. And that can be simulated, basically. So, of course, you need some connectivity. So there are challenges, of course, to always make sure that we are able to not lose a lot of accuracy. We will lose a little bit of accuracy, of course, when compared to simply solving equations, but with these RC models, what we are able is not to really get very close in terms of accuracy to the real behavior of the system. And so this is something, this is not new. This is what has been done this is known for years. In fact, this is what hotspot does, okay? And one of the things I'll tell you today is what is the difference between 3D-ICE and hotspot. So hotspot uses a similar principle. This has been there since 2006, so a bunch of years. And what you're doing in the end is you're mapping things to things. So we are mapping temperatures as voltages, and we're mapping heat flows as electrical currents. That's why we can have resistances, capacitances, and have it as a circuit. And then we solve the circuit via regular. And so in the end, what we do is basic, so it's matrix multiplications. So the thing is, all the work done so far, all the work hotspot does, for example, is for air-based cooling. But I was motivating you at the very beginning that we want to go for 3D chips. And when we go for 3D chips, and when we go for higher power consumption, our issue is that that is not enough, basically. So we need to also go into novel cooling technologies. So fan cooling has had the advantage for many years of it's relatively easy. You put fans on top of CPUs. We are used to that. We cool them down. They consume a lot of energy because air-based cooling is really inefficient in terms of energy consumption, but it solved the thing. But now we have newer cooling technologies, right? So we have water cooling, in which what we are doing is basically we are driving some water. It can be on top of the chip. It can be through microchannels in the chip, as I will tell you in a minute. And then we will be removing the heat from the processors with liquid, which can be water, or can be any other liquid that is not going, that doesn't have an electrical conductance, which is way better for electrical equipment, right? And also, we have even newer cooling techniques, such as two-phase cooling. Two-phase cooling, what it's about is basically, in two-phase cooling, instead of just simply make a refrigerant flow, what you want is that refrigerant to evaporate. Because when you go from liquid state into vapor state, you're able to absorb a lot of heat, and we are going to absorb the heat of our processors by going into two-phase, by going into vapor and then going back into liquid. I'll tell you a bit more of this with some examples, but just keep in mind that today and in the future, air cooling is not the only thing we have, right? So we need to understand how to do this. So having this in mind, what we went for is, okay, so let's assume we have 3D chips. So if we have 3D chips, we need a way to cool them down. So this was also collaboration that we had with IBM on how to build these chips, and also with ETH Zurich. And what we did is, okay, let's to that 5-tier chip that we had, what happens if we put interlayer liquid cooling? That is, we make liquid flow within the layers of our chip to cool it down. Something as you will have an inlet of refrigerant, an outlet of refrigerant, and the chip will be cooled down by this refrigerant that could be water, but as I said, could be anything else, basically. So one of the challenges of this is, of course, you need to understand what's happening, right? So it's not as easy as I will make the liquid flow and that's it. So you need to control some specific things about the coolant. You need to understand what does the inlet temperature need to be, what does the water flow need to be, and for all of these things, you need simulation, right? So this is, for example, is the example chip I was telling you about. So when I say that we are doing interlayer cooling, it's micro channels, so size of microns, etched on the different silicon layers, okay, and liquid flowing through that. So there are ways of validating this, of course. So we built the chip, we validated that it worked with real measurements. In fact, what you can see on the bottom right part is a validation we did with real cameras, etc. And the thing is that liquid cooling has very nice properties, right? Because as it's liquid, it helps us balance more the temperature across our chip, which is something that is always beneficial, right? So if you're able to balance the temperature in your chip, you can potentially bring the temperature slowly up, or at least stress the whole system, rather than creating a hotspot that is going to limit the performance of everything. So the thing is, up to that moment, okay, so we can build a 3D chip, but as I was saying, we need to have ways of simulating this. And that's where 3D-ICE came in. So basically, our goal here is, so we have this chip that you see on the right. The blue parts are the channels in which we're going to put our liquid. And what we want to do is to be able to simulate the thermal behavior of a chip with interlayer liquid cooling, which means that, different from hotspot, so it's not only now about modeling solids, it's about modeling liquids, which has some specific challenges that other simulators do not tackle, right? So we can also, what we proved here is we can also use an electrical equivalence liquid in order to model liquid cooling, so that instead of having just one type of cells with resistance and capacitances, we will have two types of cells, one for solids, one for liquids. And in the same way, we can simulate that. So that was the first version of 3D-ICE. That's what 3D-ICE did when it was born, already 8 years ago. It's been a while. So that was like 3D-ICE version 1. That's what it did. The good thing is that, well, in fact, that one was able, so it was able to match the same performance that other simulators, such as Hotspot, while also simulating liquids, which was something very fancy at that moment. The thing is that we saw that was not enough, because we wanted to simulate bigger and bigger chips. The thing is that if you're simulating just one layer, okay, it's easy. So you just simulate the thing and wait. But the more layers you stack one on top of the other, the slower the simulator is, right? So we came across with some techniques in order to find a little bit less accurate models that enabled us to win a lot in simulation times. So basically, what we call this is a two-resistor compact transient thermal model, which means instead of simulating each cell with 4 resistances as doing before, what we are doing now is just simulating the coolant flow with 2 resistances instead of 4, okay? And then we need to add we need to add some other things, but basically we were drastically reducing the computation time, meaning that we were able to get really nice speedups. So, of course, in these kind of scenarios, what we want to compare with is not only with hotspot, but also with simulators that gave us the highest accuracy, okay? So highest accuracy for us was simulators that were actually solving the specific equations that should have been put in place. So computational fluid dynamics simulations or ANSYS CFX, as I will show you later. So this was our goal, right? So to be able to, so we compare accuracy and we compare speed up against these tools that give us the best solution possible, basically. And with that, we got version 2.2 of 3D-ICE. That was our goal. And that was already 3 years ago. But we've been doing way more things, right? So just let me show you very quickly the kind of accuracy you get, okay, when you run 3D-ICE for interlayer liquid cooling. Here you have first for different water flows, because those are tuning parameters, so how fast are you going to pump the liquid through the microchannels, okay? And how much liquid are you going to pump through those microchannels? What you would obtain with ANSYS CFX, that is really the most accurate thing we could do, right? Compared with 3D-ICE. So as you can see, we were getting, for different types of chips, we were getting very nice accuracy numbers. And also with the thing that we could not only see, as I was saying, a specific point of the chip or just an average for the chip, but we can know what is the exact temperature on all the parts of the chip when the coolant is flowing through it. Okay. So we can definitely see how are we bottlenecked. And we were getting like maximum errors that were up to 3.5% when compared to the most accurate tool possible. Okay. So the goal of this, so up to here, we were covering fan-based cooling and interlayer-based liquid cooling. That was 2014. Today, what we want to do is, we know there are many, many cooling devices out there, and what we want to do is to be able to support them in an easy way. In an easy way means that I want to be able to plug into 3D-ICE anything that you want. Anything that you want, meaning you may want to simulate a heatsink, you may want to simulate a fan plus heatsink, or you may want to simulate a two-phase cooling device. And we did that. I will show you in a minute. So basically, we want to simulate all that without losing precision. So we understand also that there's a moment in which it's not enough to go into the electrical equivalent of some cooling devices. So what we worked on is something we called a pluggable heatsink for 3D-ICE that enables you to run 3D-ICE, put on top any other system that you have simulated with any other tool, and connect them together to work in a loop until convergence, okay? So that we can simulate any other system that we want. And also we wanted to validate that 3D-ICE worked in a new case that we have today, that is heterogeneous systems, right? So it's not, so we wanted to make sure that what we are doing for 3D-ICE, what we did on 2010, our validations for our chips and everything still stands when we are targeting processors of today, that we may have a mixture of different types of chips inside. So basically, the first thing, which would be the pluggable heatsink solution, what it does is, as I was saying, simply simulating, as we were doing before with 3D-ICE, but at some point, instead of keeping on simulating the upper layers, the heatsink plus the fan, what we will be doing is we will be connecting to some other simulator. Okay? This is the latest version of 3D-ICE, in fact. That's the one that you will find online very soon. We are going, as I will say in a minute, this is fully open source. You can simply get into the 3D-ICE website, you can download everything, you can run anything you want. And you can change it as you want, basically, because that's the nice thing. So we did some validation of this latest changes of 3D-ICE, as I said, on a heterogeneous system that had on the same die some ARM processors and some FPGAs. We were running that at different frequencies. And the thing is that the interesting part here is that we validated everything with real measurements, because we wanted to make sure that still it's not only about simulation. We want to make sure that we are not very far off from the reality, right? So we were able to do that by simply measuring with a very nice, complicated to use, basically, to be fair, microscope that enables us to look into what is the exact temperature inside our chip, okay? So we did that. We validated 3D-ICE against this, with these real measurements taken with a real microscope, okay? And we saw that we were still good, that our error was not going beyond 3%. This was still for a regular heatsink, but using our pluggable heatsink model. And we saw that, okay, we are enabled, so this works, so we didn't destroy anything. We are able to build on top of that, and anything that we can plug, as long as the model we are plugging makes sense, 3D-ICE will be able to give you the accuracy. So we will be able to give you 3% accuracy as long as the cooling device that you put on top has a similar accuracy than that one. So in our case, we were seeing that even for inaccurate models, we were able to reach even a 7% of maximum error. And let's recap now, just thinking about, so what does 3D-ICE offer me today? So today, basically, we have still the same capabilities that we had before. So we have 3D-ICE, it's programmed in C, it works on Linux systems. You input power traces, it gives you temperature maps, basically. Its main features will be that you can simulate regular 2D or 3D chips. You can put a heatsink on top of that can be pluggable, so you can plug it in with any other model. You can simulate microchannels, and you can simulate pin fins. All of these are examples that we are showing on the 3D-ICE guide. So all this you can launch from scratch the moment you download 3D-ICE. So simply, you can give them a go with models that we validated ourselves to make sure that you're going to get a good accuracy. So how do I download it and use it? You just go onto the 3D-ICE website. In fact, this new release, it will be fully ready by next week, when we aim at not only making it available for people that are experts on how to execute things, but to people that may not be experts on the field of thermal modeling. To make it easy, what we did is, now 3D-ICE is fully Dockerized, so you can simply download the Docker, make it run, and it will run. Okay, so no need to install complication, no need for complicated installs. And also the code is available now on GitHub, so that we want people to collaborate, to start collaborating, to start adding their own contributions to the 3D-ICE code. And all the info that you want is also available on the 3D-ICE site. Okay. So just to give you a hint of what else we can do, so basically 3D-ICE can be integrated. So we proposed a methodology on how to integrate 3D-ICE into complete flows for MPSOC thermal simulation. So basically, you can even integrate it with the schedulers, because you can make 3D-ICE run in a loop, and you can test different power management policies with 3D-ICE to understand how is your chip behaving during runtime, and see the influence of your workloads on the system and on the thermal profile. As a proof of concept, we also validated this with a two-phase cooling device that is named the Thermo Siphon. Thermo Siphon basically is this thing that you see here spinning. The Thermo Siphon is basically a two-phase cooling mechanism. You put it on top of any CPU, as long as it matches a certain power value. So you put it on top of a CPU, and then there's a flow in which there's a refrigerant that evaporates and condenses by itself. So we plugged the Thermo Siphon with the pluggable heatsink of 3D-ICE into 3D-ICE to make it work. We are just working, we are finalizing this proof of concept. So far, we're getting very nice and very promising accuracy results for this. And we will soon, in fact, also free models for all of this. So as conclusions, we have version 2.2.7 of 3D-ICE. It will be available on the site next week. We are able to simulate any cooling device that you want, not only that we want, because you will simply be able to connect it. And we will also provide some new features for cooling. Just to give you some numbers, we have like 1,500 people that downloaded 3D-ICE. We have above 300 citations, so we believe that we have like among 200 active people researching on the field, downloading and using 3D-ICE. And we want to enhance that. So we want more collaborations than ever. That's why we are trying to let you propose your own cooling systems. Next release will come with more cooling devices. So we will give you ourselves some things that you can test. We'll give you fan models, we'll give you microfluidic cooling models, or even two-phase liquid cooling models so that you can test how it works. And finally, so I just wanted to finish by letting you know who is the team that made all this possible from the very beginning right up to today. Thank you.